Okay, so this is our project 4 code. We're in our driver right now. We're set up to run a categorical set, our car data. We're going to run that on our genetic algorithm tests. So we're going to go ahead and give this a run. Then you can see that it's going to output our loss function results for hidden layers with 0 hidden layers, 1 hidden layer, and 2 hidden layers. You can see we get precision, recall, and accuracy, and we get a range and then the mean for our tenfold cross-validation sets. If we hop on into the genetic algorithm itself and we look at this mutation function, we can throw a couple breakpoints in here. And if we run in debug mode, we can take a look at how some of these values change with time. If we look at these weight values as we iterate through this for loop, the genetic algorithm is doing its work. We can see these weight values are changing. And then if we come over to the crossover function in the genetic algorithm, throw a couple more break statements in there, breakpoints, and we can look at these two weight hash maps. We can see that the swap function, if the crossover chance it hits, some of these values in these hash maps are swapping. Now if we head back to the driver, this time we're going to set up to run on the segmentation set. It does well for this, for these particle swarm tests. So we're going to go ahead and give this a run. Then we can see very similar output we're going to get. We're going to run again for hidden layer 0, 1, and 2. This time we're going to print out each of these cross-validation sets, and you can see precision, recall, and accuracy for each of them. And then in our final results, we would just average those, and you can see it would work for 0, 1, and 2 hidden layers. So if we hop over to the particle swarm algorithm itself, and we look at our swarm function, throw a breakpoint in there, and then take a look at this in the debugger. Pull it up a little bit. We can look at this group best score and see as we iterate through this swarm function that group best is being updated every time a new best score is found. And we've got an improvement counter, so if that gets too high, we just call it and we realize it's not going to improve anymore. We can take a look at these personal best scores and see how they change as well. Now if we look at this update velocities function and throw a breakpoint in there, take a look at that in the debugger, we can get a better look at some p-best and g-best values and how they change when this current value is changing, and see that these velocity values are set by clamps that are tunable parameters that we've tuned. You can see these p-best and g-best values updating as the current does as well. Now if we come back to the driver, looking at the segmentation data set again, which is categorical, we're going to run on our third evolutionary approach, which is the differential evolution. Look at our tests, very similar output. We're looking at 0, 1, and 2 hidden layers, and we're going to get our precision, recall, and accuracy loss functions. And this is going to print out for each of the tenfold cross-validation sets. So there's going to be 10 of them for each hidden layer, for each data set. And then for our results, we would average these once again. We'll go ahead and show hidden layer 1 starting, and then we'll take a look at the debugger. So inside the differential evolution algorithm itself, we're going to look at the evolve function here and throw a breakpoint in this nested for loop and see what happens with these mutant values as we iterate through this for loop. So we see that they're mutating over time. All these weights stored in this array list. As we iterate through, these values are changing. And then if we come to this create trial function over here and put a break point in this for loop as well, we can look at this crossover chance, and we can see that it changes over time, and when we get a new mutant like we did just there, it's going to reset and then start changing again, and that's initialized by a tunable parameter as well.